Okay, hello, good morning, good afternoon, everyone. We are ready to start. Welcome, everyone, and thanks for joining Neuroelectrics webinar again. My name is Rafał Nowak, and I will be your host today. So today we'll be talking about transcranial alternating current stimulation. First simulate, then stimulate with the intriguing title. So I'm very happy to welcome our guest speaker, Professor Christoph Herrmann. Hi, Christoph.
Hi there.
Good to have you here, Christoph. We'll begin with Christoph's presentation, and this will be followed by Q&A period. So please free to submit your question at any time using the Q&A tool. So please let me quickly introduce our speaker, Professor Christoph Herrmann. Christoph is a professor of experimental psychology at the Carl-von-Ossietzky University in Oldenburg, Germany. He received diploma in electronical engineering in 1992 and Ph.D. in computer science in 1996, both from Darmstadt Technical University in Germany. In 2002, he received his habilitation in psychology from Leipzig University in Germany. From 1997 to 2002, he was working as postdoctoral researcher at Max Planck Institute of Cognitive Neuroscience in Leipzig, Germany. Then from 2003 to 2009, he was a professor of biological psychology at the university in Magdeburg in Germany. And since 2009, he's a professor for experimental psychology at the Carl-von-Ossietzky University in Oldenburg in Germany. He's author of more than 150 journal articles, holds multiple patents, and his research interests include brain oscillations and cognitive processes, as well as their manipulation with transcranial brain stimulation. When he's not working, he likes to play golf and sailing. So obviously a lot of shared interest with us here at Neuroelectrics. Welcome, Christoph, all yours.
Yes, thank you, Rafał, for the kind introduction. And hello, everybody. And good afternoon if you're in the same time zone. And maybe it's interesting for Rafał, as a little side note, we actually used your stimulator on the golf course already for a study trying TACS on the golf course. But this is not what I'm going to be talking about today. What I will be talking about today is the following. I would like to introduce you to a couple of the methods, brain oscillations, what is resonance, what is entrainment, and why is there an after effect after the end of stimulation. Then that's all theory. Then I will introduce you to a couple of physiological experiments on the after effect, but also on the online effect, and then some cognitive experiments, and in the very end, also a preliminary study on a potential future application. All right, here I would like to explain to you the difference between a resonator, on the next slide, an oscillator. Almost everything that we have in the world can be made to resonate. You know this phenomenon, for example, from a glass of wine. And if you either rub the rim of the wine glass or if you sing at it, you can make it oscillate. This is not an oscillator because it doesn't oscillate at rest. But if you can make it oscillate, it does so at a so-called resonance frequency. And depending on what frequency you drive it with, you see different amplitudes. And if you drive it at its own resonance frequency, you have the highest amplitude that's shown over here in this kind of spectrogram. But it always resonates at the driving frequency. It doesn't have an intrinsic frequency. And therefore, such a passive system cannot be entrained. But what is more interesting is an oscillator, because it can be entrained, and a typical system that would be such an oscillator is a pendulum clock, for example. So it oscillates at rest and has an eigenfrequency at which it oscillates. That's the intrinsic frequency, if you want. But you can also perturb it or drive it from the outside with an external frequency that's called the driving frequency. So here you could either see the eigenfrequency or you see the driving frequency. And in such systems, it's possible to entrain these systems. And I'm telling you this because this is the assumed mechanism behind transcranial alternating current stimulation, or TACS. And here you see a further aspect of entrainment, where the strength of the stimulation determines whether the system will be entrained or not. I'll start on the right-hand side and show you what I mean by entrainment. So here we have the driving force, that's a sinusoidal current, for example, and here we have the spiking of neurons. And in the entrained case, you can see that the spiking happens during the peaks of the sine wave, but not during the troughs. And down here, you see the case where we don't have entrainment. Here, the spiking of the neurons is not related to either the troughs or the peaks of the sine wave. Now, this can be coded in two colors in this so-called Arnold tongue, where you have the frequency of the driver on the horizontal axis and the strength of the driving. So in case of TACS, the milliamps on the vertical axis. And you can even achieve driving with very weak intensities if you're exactly at the frequency of the oscillator. So for example, 10 Hertz for the human alpha activity. And if you make the driving stronger, you have a wider range of frequencies where you can achieve this entrainment. And this whole thing is called the Arnold tongue, the region where we see entrainment. And here in the lighter gray, you see the regions where we don't have entrainment. Now we used a artificial neural network in order to find out whether, at least in a simulated brain, this is actually what TACS would do to the neurons. So we had 800 excitatory neurons and 200 inhibitory neurons that were coupled together. And the probability of the coupling was higher for short axons with fast propagation delay and less for slower axons with longer delays. And I'll skip what you see here. That's not so important. We'll go to the next slide and see three different things. So if we leave this artificial neural network alone, it shows an oscillation, which has a frequency of roughly 10 Hertz in the spectrum. And here you see all the different neurons, and there's a little black dot when they actually fire. And you see they do so 10 times a second, so this is the 10 Hertz. And now, if we, in addition, stimulate the network with what you see here in light red, that's a 10 Hertz impulse train, you can see that the 10 Hertz is amplified and it's more regular, the firing. And now we can, of course, use many different frequencies to drive this toy network. For example, here we use 17.5 Hertz stimulation, and you see the average of all the neurons changes. And here you see the biggest peak at exactly half of the driving frequency. You also see a small peak here at the driving frequency. That's something that's to be expected of a system that shows entrainment. So if you drive it with 18 Hertz, you'll see half of the driving frequency, so 9 Hertz. If you drive it at 20 Hertz, you'll see 10 Hertz. If you drive it at 22 Hertz, you'll see 11 Hertz. So here we show only a few frequencies, but here I can show you many different frequencies. So on the horizontal axis, you see the 100 different frequencies that we use for the driving. And here you see the amplitude that we used for driving. And then the top diagram A, you see the power that we saw, and you can already see, aha, here are these Arnold tongues that I was referring to, not only the one at 10 Hertz, but there are also further Arnold tongues. And in the lower diagram, you see the frequency of the driven system. And if these black lines outline the Arnold tongue, you can see inside the Arnold tongue, the frequency changes from roughly 5 Hertz is blue to maybe 15 Hertz is red while you go through the tongue. So we think that this is evidence that at least in a simulated neural network, this is how TACS entrains the neurons. Now I have the subtitle, simulate before you stimulate. The previous simulation is something that you should know about it, but you don't have to do that every time yourself. But actually, it does make a lot of sense to use a finite element model, and the tools are freely available in the net to actually simulate where the current flow would be depending on the electrode montage that you use for stimulation. And here's a study by Florian Kasten that shows a couple of nice features. At first, I'll show you here, these two black electrodes are the stimulation electrodes at electrode position CZ and electrode position OZ. And here you see the finite element model of the human brain. And the warm colors represent current flow and the blue colors don't. So you see there is current flow between the two electrodes. We're doing this in the MEG because the sensors are not connected to the skin, and therefore the artifact by the stimulation is not so bad on the MEG. Now what Florian did was that he recorded the MEG of 40 subjects and did a frequency analysis to find out people's individual alpha frequency, and then later on stimulated them. And at the same time, he put the people in an MR scanner and recorded T1 images to create a head model for a beamformer. And then he localized this individual alpha activity to have the source in the headspace. And then he used the ROST toolbox, which is freely available, to simulate where and how strong the E field would be in this very subject, which depends on skull thickness, etc. And then he correlated these images because they're now in the same space, and computed a multiple linear regression analysis for the TACS condition and for the sham condition, and had the factors spatial correlation between these two brain images, then the frequency mismatch between the alpha frequency and the simulation frequency, and the intensity of the E field, which was different in every subject. And that was significant. And now I can show you what happens for the different conditions. So for the TACS, you see a very nice correlation between the power that was predicted by the model and the power that was actually observed after the end of stimulation in the data. And here you see for the sham condition, there was no such correlation. So the conclusion is that for one thing, you should of course match the pattern of current flow to the source of the activity that you want to modulate, but also by doing these computations, you can already predict whether you're going to have a strong effect in this single subject or not, or at least later on you can explain why maybe in some subjects it didn't work, which is something that usually happens in our experiments. Now there's one further thing which I want to introduce before I come to an interim conclusion. That is the funny thing that we see an effect after the end of stimulation, not only during stimulation. And that is probably brought about neuroplasticity. And we also did a simulation to understand that. And we used something that's called spike timing dependent plasticity. I'll explain that up here. So we look at this synapse here between these two neurons. So to this synapse, the left neuron is the presynaptic neuron and the right neuron is the postsynaptic neuron. And now we look at different cases. So here on the right, we have a spike arriving from the presynaptic neuron, and afterwards the postsynaptic neuron spikes. So this could have been causal. And in this case, the strength of the synapse is actually increased the more these two are in temporal synchrony. However, in the opposite case, if the postsynaptic neuron spikes first, and then afterwards a spike arrives from the presynaptic neuron, this could not have been causal, and then the synapse is weakened. Now we built a little toy network of many different loops. We had one neuron here in gray at the top that was stimulated with 10 Hertz. And then we had multiple different neurons shown here in blue and in red. And we had different conduction delays on these axons. So there would be little loops. And here the turnaround time is about 80 milliseconds before the action potential comes back. Here it's 100 milliseconds, so that corresponds to 10 Hertz. And here it's 120 milliseconds, so that correlates to 8 Hertz. And what we did is we had many different weights that were randomly assigned to the synapses. These are the gray dots. Then we did the stimulation for a while and adjusted the weights according to this learning rule. And then we have the black weights after the end of the stimulation. And here you can see the synaptic weight was before stimulation on the average 4. And wherever it's above 4 afterwards, we say, well, we did achieve long-term potentiation. So that's this red region here. And if you look at the frequency of that, for a 10 Hertz stimulation, we changed all the weights that were in loops that were incorporated roughly between 10 and 12 Hertz. That's interesting to know because now you have two different predictions for what exactly you want to optimize. You can either optimize the online effect based on the idea of the Arnold tongue, and then it is most effective if the driving frequency is exactly at the eigenfrequency. So you should record the EEG, look at, say, the individual alpha frequency and stimulate with that, or you use an integer n/m ratio of that, and then you are in one of the other Arnold tongues. However, if you want to maximize the offline or the after effect, then it's most effective if the driving frequency is a little lower than the eigenfrequency of the system that you're targeting. And actually, an experiment by Alexandra Vossen showed that in the data. So now we'll come to the first physiological experiment and the after effect in the EEG. So this is something that we did back in 2010. We determined the alpha activity. We determined the threshold for sensing that there is an electric current flowing through the skin, and a phosphene. You see a slight flickering if you stimulate over the back of the head. Then we recorded 3 minutes of EEG, did 10 minutes of either stimulation or sham, and looked at the EEG afterwards. And here you see the montage. This is what we found in the EEG. So on the left, you see the spectra of the TACS group before and after stimulation. And here you see the sham group with no differences. And here you do see an increase from before to after stimulation. And here it's not so clear because here they were all just mapped into one spectrum, even though they were stimulated at different frequencies. But if we take the stimulation frequency of every subject and put that into a t-test, you see that there is a significantly higher increase in the TACS group as compared to the sham group. Now, we only looked at 3 minutes of this after effect, but we wanted to know how long does this after effect last. So we did a similar experiment, but now we recorded 30 minutes of EEG after the end of the experiment. And in this case, the task was an auditory task, but the montage was from CZ to OZ. And here's what we found. There was one more surprise in this experiment. So let's at first start on the left side. We decided we performed the experiment with eyes closed, and that's why we used an auditory task, because then you have a nice alpha peak and it's easy to determine the frequency. But you can also see that in the sham group and in the simulation group, there is a high alpha peak, and we were not able to amplify this peak by TACS. However, when we repeated the experiment with eyes open, then we see what we saw in the previous experiment. We see a bigger increase in the TACS group than in the sham group. And here you also see why it's always important to have a sham group, because even in the sham group, you see an increase of the alpha activity from before stimulation to after stimulation, because whenever subjects sit in the room for an hour, their alpha activity will just increase over time with their boredness. So the ability to drive the alpha is also state dependent, for example, depending on the amplitude of the alpha before they even start the experiment. And then we decided, oh, here's just the over the course of time. So here you can see that the increase of alpha activity lasted for 30 seconds and did not stop. And therefore we set out to do the experiment for an even longer time. So now we went back again to a visual task. We had the OZ, CZ montage, and now we recorded 90 minutes of EEG. And of course, we expected to see the increased alpha activity in the beginning and to see it decrease after some time, which is not exactly what happened. So here you see again the alpha activity for the stimulation group in red and for the sham group in blue. And you can see for quite a long time, you have a difference between the two. But then after about 70 minutes, what happens is not that the alpha activity of the stimulation group returns back to baseline, rather the alpha activity of the sham group also ramps up over time, and eventually they are no longer significantly different. So for 20 minutes of simulation, we get an after effect of 70 minutes. And currently some colleagues are trying to extend this by stimulating multiple times over multiple days. And now I'll show you that you can also look at the online effect of TACS, and we used MEG for that purpose, because in MEG, as you see here, the stimulation electrodes are on the skin, but the sensors of the MEG are not touching the skin, so you see less of the artifact, and it's easier to get rid of, because when you use a sine wave to stimulate, you always see the sine wave in the EEG. So here on the right, you see the topography of a visual P1 and auditory N1, but it's actually not to be seen, because what you see are the two cables that go from the stimulator to the stimulation electrodes. But using a beamformer, you can actually separate the sources that are inside the sensors from those that are outside the head. And of course, these cables are outside the head. If we look at the spectra, this is the sham group, and you see with eyes closed, they have a higher alpha peak than with eyes open. And here you see during TACS, this is much higher, so you only see the artifact and you see no difference between eyes open and eyes closed. It's just always the same 10 Hertz artifact that we stimulate from the outside. But when you transform this into source space with the beamformer, here you can see basically the same higher activity for eyes open than for eyes closed. And here, even for TACS, you can now see, yes, we see alpha activity. It's higher for eyes open than for eyes closed. And if you compare it to the sham condition, you also see that the alpha activity was amplified by TACS. But of course, that is quite tricky to do and requires an MEG. Now, I also want to show you some cognitive experiments, because our goal is not to modulate EEG activity for the sake of having modulated EEG activity, but as I showed in the very beginning, we think that brain oscillations are responsible for many cognitive functions, and we want to change or restore cognitive functions by changing brain oscillations. So we'll start by showing that alpha TACS can modulate mental rotation. That's again this experiment done by Florian Kasten. And he did a mental rotation task, which you can see down here. So he shows two of these cartoon images. And what the subjects have to indicate by a button press is whether they are the same or different, but it could be the same and rotated. So here it's clear they are the same, but here it's a bit more tricky to see whether they're the same or not. So they did one block of this experiment before stimulation, then they did 2 blocks during stimulation and another 5 blocks after the end of stimulation. And we want to see whether the stimulation influences the performance. At first, we look at what happens to the EEG. So in the baseline and after block 4, we can record the EEG because there's no stimulation. And this is a so-called time frequency plot. So on the horizontal axis, you see the time relative to the onset of the visual stimulus. On the vertical axis, you see the frequency. And here in the colors, you see whether the frequency is high or low. So blue means there is a reduction, and this is in the alpha range. So after the visual stimulus comes on, there is an event-related desynchronization or a reduction of the alpha activity. And you can see that this is stronger here than before stimulation, and for sham, this is not the case. And here you see this as a time course, or for the sham group, this just goes up and down at like 100% of the baseline, but it stays elevated for the whole time for the stimulation group. And this is actually the type of activity that was shown by Christophe Michel to be responsible for the mental rotation, for the performance in the mental rotation task. And here you see the performance of our subjects in the task. So they had a performance increase of roughly 10% due to the stimulation. And here you see this as a time course. So baseline was defined as 100%. And you see already during stimulation, the stimulation group improved. And this improvement stayed there after the end of the stimulation for the whole 5 blocks. So this shows nicely that we can not only modulate brain oscillations, but also cognitive performance that is related to brain oscillations. And I'm going to show you 2 more examples where spatial attention can be modulated. So this is a bit more complicated. It has been shown that when you attend to the left hemifield, then the stimuli that are processed in the right hemisphere, when you have attention here, the gamma activity goes up and the alpha activity goes down. And of course, vice versa for the other field. And therefore we thought, well, we'll try to change the performance of attention by stimulating the hemispheres with either alpha or gamma TACS. And at first I'll guide you through the hypothesis because it's sort of fourfold the hypothesis. So here we stimulated the left auditory cortex with alpha activity. So we reduce attention if you want, or we inhibit the left hemisphere. And these are attend left trials. So what arrives in the left hemisphere are stimuli from the right ear. And for attend left trials, these are distractors. If we, however, stimulate the left hemisphere with gamma activity and have attend left trials, then we facilitate the processing of stimuli to the right ear, and they will then be, again, distractors. Now we go to the other type of trials, the ones where you're told to attend to the right hemifield. And then if we stimulate with gamma activity, we facilitate the processing. And what comes from the right ear to the left hemisphere will be the targets, where here with alpha activity, we inhibit the targets that come from the right ear to the left hemisphere. So this is the pattern of the results that we expect to get. And I'll put the results right on top of this expectation. You can see we have this differential effect between the alpha activity where performance gets worse in comparison to the gamma activity where the processing gets better. So that was very nice. And we tried that at first for auditory attention, but subsequently we also tried that for visual attention. And again, it's a bit of a complicated hypothesis. So here you see the visual stimulation. You have a cue that indicates where you should shift your attention. And then the target that you have to detect can either be on the attended side or on the unattended side. So that's an invalid trial. And here you see the same again. And now if we stimulate the left hemisphere with alpha activity, we expect the reaction times to go up. If it's a valid cue or if it's processed in the other hemisphere to go down, and the opposite pattern for gamma activity. And the whole pattern changed if you do that ipsilateral to the cue. And I'm not going to show you the whole series of results, which is a bit complicated. Have a look at the paper if you like it. You can download it. It's public. But we did find this differential effect for the alpha versus the gamma stimulation, but only for the endogenous shift of attention, not for an exogenous shift of attention that we didn't show here. And it was specific to the left hemisphere, indicating maybe that the left hemisphere is more important for shifting attention. Now, finally, I would like to show you something where we tried to do a first step into therapy with TACS. It is known that in ADHD patients, especially in adult patients, the P300 in response to targets is reduced in amplitude. Now you see on the left-hand side a P300 in response to a visual stimulus. And this is the sort of time domain representation, but you can also view this as an event-related oscillation and look at it in the time frequency domain. And then the P300 is an event-related oscillation with a certain frequency here, roughly in the delta to theta frequency range. And the red cross indicates the peak of this event-related oscillation. So our idea was to use TACS to individually amplify this oscillation and then see whether we could elevate the P300 amplitude in subjects and maybe even influence their processing. And again, it's a bit of a complicated design. So maybe we'll start here and we look at a typical P300 scalp topography with a PZ maximum. Now we tried to use an electrode montage that mimics this scalp topography. So we have 12 simulation electrodes, which are shown in blue and in red here. So blue is the positive half wave of the sign, and red is the positive half wave and blue is the negative half wave. The white electrodes are not stimulating. And if you do this, then you get exactly this topography. And you hopefully agree that this is somewhat similar to the P300 topography. Down here, we see how this is converted to voltages on the cortex or to current density in the brain. And this is also the region that has been found as the P300 generator in fMRI studies. Now, the simulation is a sine wave that is running all the time, but we're presenting our stimuli in a specific way such that the P300 comes at the same time as the positive half wave of our TACS simulation. The TACS stimulator always gives us a trigger, that's the blue line here, when there is a zero crossing from negative to positive, and then we compute how long we have to wait before the stimulus is presented to have the sine wave coincide with the P300 latency. That you have to program once beforehand, but then this is done automatically during the stimulation. And this is how the results look. So here we have the sham group, and you don't see a significant difference on the P300 amplitude from before to after stimulation. And in the simulation group, you see a significant enhancement of the P300 amplitude. And luckily, we also saw that they had a decreased error rate in our target detection task. So they had to identify O stimuli among X distractors. So we hope that in future, TACS can be used to restore disturbed brain oscillations and in turn disturbed brain functions. With that, I would like to thank you for your attention and the members of my group for doing the studies that I showed to you. Thank you. Now I'm just stopping my presentation, is that right?
Perfect. Yeah, otherwise you can keep the photo, very nice photo, you can have a nice picture if you want, so you present to everyone.
Sorry, I was too fast.
The whole your group. Thank you very much for excellent presentation. So we are ready for questions. So you can use the Q&A tool. We have already some questions. We have some question in the chat as well. So let me only first to do like a general question related to TACS stimulation and the never-ending questions related to if the observed changes in MEG alpha, for example, what you are presenting are related to cortex stimulation or to the peripheral stimulation, so the cranial nerve stimulation. So you're using always as a sham and not using the peripheral nerve stimulation with lidocaine, for example, and anesthesia in TACS. So how can we be sure that this is related to cortex stimulation and not the peripheral nerve stimulation?
This was also done in the study by Florian Kasten, that he tried to simulate the skin effects. And he had that also in the model, and he tried to explain the effects that he did find in his data with the cortical stimulation intensity and its variety, or with the intensity of the skin stimulation and its variety. And the skin simulation didn't do any predictions, but the cortical simulation had a nice prediction, as I showed. I didn't show the part about the skin stimulation. But I think there's also a monkey study recently that did the lidocaine and that showed that, I don't know exactly how they did the study, but that was also quite convincing that it's actually the cortical stimulation due to TACS that gives rise to the effects and not the skin sensation.
Okay, so with this, we can actually read out the effect of cranial nerve stimulation, of peripheral stimulation, without the need of using another control group. And actually, you have shown this in the paper by Kasten et al. That you can even model this and predict, and with you are predicting that there is no peripheral effect. We cannot assume to be based on the peripheral nerve stimulation. And the second question is, so you were, I was trying to count the potential causes of TACS variability and related to individual changes in responses, and based mainly and related to the head anatomy. And this is leading to change in the electric field strength as a first, then the spatial distribution of electric field as a second. And there is a mismatch between TACS frequency and the targeted oscillation as a third factor that influences the effect and variability in TACS. Would you say that any one of those three is more important for TACS, that we should take care more preparing our experiments?
That's a good one.
All are probably important, but you are taking care very much about the target frequency. No, you are measuring before.
Yes, but we also put a lot of effort into finding the source of the brain oscillation and matching our electrode montage such that we actually stimulate this very region and not just some other region. So this is equally important, I think. If you have a process in the right hemisphere and you stimulate the left hemisphere, you can't expect it to have any effect. And the better the spatial overlap between the source and the pattern of current density, the higher the after effect, at least.
Okay, so your answer is that we should take care of all of these factors and use modeling, and also record the ongoing activity. So actually, there are questions from different attendees, Lucas and Anand, regarding the intensity of the stimulation in TACS in your experiments, especially together with MEG. What is the intensity in milliamperes? And if there is a change if you can expect the change of the effect in alpha activity, for example, changing the intensity of the stimulation.
I think in the MEG study, it was 1 milliamp peak to peak.
Okay, and then if we increase the intensity, should we expect the increase in the effect of alpha, for example?
Yes, definitely we would increase the effect. But the problem is that at high intensities, for one thing, you can no longer hide the fact that people are in the stimulation group and not in the sham group, because you just feel a tickling sensation under the electrode. And in addition, if we go up to something like 4 milliamps, our subjects do not tolerate the tickling sensation anymore. So even at, let's say, 2.5 milliamps, you can still do that. They will cope with that. But it's much harder to fool them. So our sham condition is not just completely shut off, but we ramp in and ramp out the current for some 30 seconds in the beginning and at the end of the 20 seconds, because in the beginning and in the end, the skin sensation is the strongest. But if you have more than 2 milliamps, you basically feel the sensation all the time, and you can't sham it anymore. Or it's harder to sham. You'd have to use lidocaine cream under the electrode or things like that.
Okay, thank you very much. The question from Mohammed. What is your hypothesis of why gamma TACS is facilitating one hemisphere but reducing other? The same with alpha.
No, sorry, that was a misunderstanding. So let me try to repeat that. If I attend to the right hemi field, the stimuli that come from the right hemi field will be processed in the right hemisphere. And now it has been shown that during attentive processing, the gamma activity goes up and the alpha activity goes down. And if we're now applying alpha TACS to the right hemisphere, then we think we're reducing the processing. And if we stimulate with gamma, we facilitate the processing. The same would happen if we stimulate on the other side, but in the experiment that I showed, we stimulated only one hemi field. Maybe this is clearer now.
Yeah, okay, actually there's another question related to this with the same misunderstanding, I guess. A question from Wang, actually referring to page 37. It seems like the amplitude in baseline between sham and stimulation groups are different. Do they have significant difference? Thank you. Actually, yeah, this is the general question regarding the importance of the baseline between in the real group and re-stimulation group and sham stimulation groups.
I don't know by heart which is page 45, but I think it's the ADHD group, and we did test that. So yes, descriptively, it's different. And this is something that, of course, always happens by chance, that they're not identical, but it was not significantly different.
Okay. A question from Mimin, why 10 Hertz is important? Have any evidence from in vivo study? General question, why 10 Hertz is so important?
Let me also rephrase that. So we used 10 Hertz because with 10 Hertz, or we used the individual alpha frequency because the individual alpha frequency is something that you can identify very easily in the EEG. That's why we didn't start with more tricky frequencies like gamma activity. And what's important is that you stimulate at the frequency which is related to the cognitive process. So if you have a process that depends on alpha activity, you should stimulate with the individual alpha frequency. However, if you have a cognitive process that relates to motor activity and therefore maybe beta oscillations, then you should stimulate with beta activity. Or if it's related to attention and it's related to gamma activity, then you should stimulate with gamma activity.
Okay, thank you. Question from Ika, in the ADHD study, you said that medication of the patients were discontinued. Are there any known contradictions for psychiatric medication and TDCs, TACS, or just that it has not been studied sufficiently? It's actually the effect of the medication, if it should continue with medication, for example, in the ADHD group or in autism.
I'm not a medical doctor, and I'm not into the drugs and their effects. I couldn't say whether there are contraindications of the drugs and the stimulation.
Okay. Next question from John. Great talk, Christoph. The greater alpha modulation for eyes open versus eyes closed, is your interpretation that the brain is more locked in when alpha is stronger? Could you comment on the significance of this in general? In example, common practices of looking for strong peaks for phase-based stimulation.
I'll try to rephrase it maybe, and maybe then this is also a misunderstanding of what I said before. So when we close the eyes, the alpha activity increases in amplitude. And we found that in this state, we can not further increase the amplitude by alpha TACS. Now, there are two potential explanations. It could be that the alpha activity has a ceiling effect and could not be elevated more than that. So it's the maximum that you can get out of the alpha. Or the other explanation would be that our intensity is not big enough to elevate it even more. And of course, we're not sure which of these two explanations are right. But maybe now that I said it in a bit more detail, it becomes clearer.
Okay, that's perfect, thank you. Question from Ika, have you explored the phase synchrony between the stimulation and underlying EEG waves?
That's the tricky part. I know your device can do that. We have another device with which it's very tricky to look at the EEG during stimulation. We have done that, and we have used multiple tools to get rid of the EEG artifact, but the EEG artifact is so much bigger than the EEG. And when you try to subtract it out, there is usually some residual artifact remaining in the EEG data. And if that's on the same order of magnitude as the activity that you're trying to record or modulate, then it's very easy to mistake the artifact for elevated alpha activity and see that it's in phase and so on. So we think that we can show that, but that's not due to papers that I show today. But it's a very tricky endeavor. Let's put it that way.
Okay, and actually the same for MEG. So you are doing the same with MEG, and then you can expect even more artifacts, I guess, in magnetometers and radiometers.
It's a little, the artifact is actually smaller. And for the MEG, it's easier to get rid of the artifact with the beamformer.
Okay.
But also for both of these papers, so we have a similar EEG paper. There were other groups that tried to replicate what we did and get rid of the artifact, and they actually showed that in their approach to do much the same as we did, they were not so successful to get rid of the artifact.
Okay, and you are never afraid that you will saturate the magnetometers or radiometers in MEG being so close to the sensor, actually generating huge magnetic field somewhere?
Yeah, that's a nice anecdote, actually. I asked my previous mentor, Burkhard Mees, who is the head of the MEG group in Leipzig, where I learned to work with the MEG, whether I can take a TACS device into his MEG, and he was like going crazy. Oh my goodness, 10 years ago, I didn't even allow you to take an LED into the MEG, and now you want to take an electric stimulator in there? No way. And then we actually did this together with Nathan Weiss, who then just had an MEG in Trento, Italy. And he said, I really like the idea of doing that. And it could happen that the sensors catch flux, but we'll just do it 1 week before we have the annual maintenance. And if the sensors catch flux, engineers have to get rid of it.
Anyway, we'll get dry. So you will have to refill, and then you will reset.
But actually, they did not catch flux.
That's great. That's great. So you are not generating the huge magnetic field. It's actually a question related to beamformer from Shuka. If you use a beamformer to suppress the TACS noise in order to investigate the online effect of TACS, what do you expect to happen to the secondary current of TACS? Are you assuming that the secondary current is not included in the measurement signal, or do you think it can be suppressed by the beamformer?
What is the secondary current?
So I don't know if he understands to the primary and secondary currents at the neuronal level, or secondary current generated by TACS.
I can't read the question. I don't see all of the questions.
This is in the chat. Actually, we have some questions in the chat and some questions in the Q&A.
Okay.
So if you go to the chat at 7:34.
There's so many chats. I don't find it right now.
Yeah.
Let me just guess what might be referred to. Maybe the primary current is meant the current that flows in the wire, and the secondary current is the current that flows in skin and head. Well, of course, the one that flows in the skin is not interesting for us, but the current that's flowing in the cortex, maybe that's what he's referring to.
Probably.
That's something that comes from inside the head. And yes, the beamformer supposedly separates the current that flows in the leads, which is an artifact that we want to get rid of, and the current that actually flows inside the cortex and interferes with the brain activity.
Okay. So question from Muresa. Thanks for the great talk. Sorry. What's your idea of TACS and cortical traveling waves? It's a general question regarding traveling waves in the brain and then trying to modulate this traveling waves through TACS.
Well, if you have a traveling wave, you want to interfere with it, you would have to know where it is at the time of stimulation. That's a little bit similar to trying to stimulate in or out of phase with an ongoing oscillation. In order to do that, you would have to be able to record and stimulate at the same time. So if you have a device that gets rid of your artifact and you can actually see the brain activity and then stimulate, then that's fine. We weren't so successful with that yet. We tried to do what we call closed loop simulation. So record the EEG activity and adjust the simulation parameters to fit to this ongoing oscillation in some way. So same frequency or in phase, out of phase. But we actually didn't achieve that. And we did something that we called interleaved closed loop simulation. So we have a few seconds of recording EEG without stimulation. And then we stimulate, but we don't analyze the EEG. That is the closest we were able to get to so far.
Okay, thank you very much. A question from Jimin. Is there any advantage using TACS over TDCs in modulating time domain features of EEG as tried in ERP of ADHD experiment? What will happen if you will use, actually why you are using TACS instead of TDCs, and what are the advantages of using TACS to modulate ERPs?
Well, maybe I'll start a little more general than the very question. So TDCS is more intended to change the excitability of a cortical region. So you have one electrode that's over the target region and maybe a bigger return electrode somewhere else where you expect weaker effects. And if you have an anode here, roughly speaking, you would increase the excitability. And if you have the cathode here, you would reduce the excitability. TACS is a bit different because it's not about the excitability of the target region, but at first you identify a brain oscillation that has to do with your cognitive process. And if you find that gamma activity has to do with attention and it happens in the primary auditory cortex, then you try to place your electrodes such that the stimulated region matches the generator of the gamma activity, and you match your frequency of the stimulation to match the frequency of the gamma activity. So they're slightly different concepts, the TACS and the TDCS. And since we believe the P300 is an event-related oscillation, we thought, well, let's use TACS at the frequency of the P300 in the delta range.
Perfect. Thank you very much. So very clear explanation going even to DCS. So I think we are running out of time. So with this answer, we can close our Q&A session. So thank you very much, Christoph, for your presentation.
Thanks for having me.
Yeah. Thank you for joining us. You are always welcome, and you have so many interesting things to explain. So we'll be happy to have you again here, maybe within a few months. I also want to thank everybody for joining us today. I hope you will join us again for the next webinar. Please visit our webpage at neurolexics.com, where you will find more information about upcoming webinars. And once again, thank you very much. Have a great day. We'll see you next time. Take care and goodbye. Thank you, Christoph.
Bye, and hopefully see you soon in person.
The same. Thank you. Bye.